All right, so if we want heat to be used to do work, our general case for that is that heated gas moves a volume or a surface. What we're doing is utilizing pressure to apply a force. And if by increasing the pressure, we're utilizing more and more and more pressure that can apply a force to an object. That's really what we're doing with heat doing work. So boiling water to turn a turbine. So for a simple diagram of a heat engine, all right, this one was a closed system, I think, that we saw in our notes. We have a boiler. We'll put a little fire underneath of it. So we've got heat in. It's got water. We'll put a little spout there. As that water boils, it's going to turn some kind of fan device. So if we put a fan with little turbine blades in there, that boiling water heats the fan, and then that steam escapes. And what we'll do with that steam is condense it somehow. So we'll make this area here cold. To condense the water, it's going to go back, get heated up, rise as steam, and the force of that steam is going to push the fan blades. And this spinning, that's the work, or that's the engine part of it. That's one way that we can do it. Other examples of heat engines, this is a steam engine, obviously. Your internal combustion engine in your car is a heat engine. And your diesel engines are heat engines. So those are some examples of heat engines that don't use steam. All right, that's our heat engine. Why does the temperature of the heat engine need to be higher than that of the cold sink? The cold sink, its whole job, whatever, the surroundings is how I like to think about the cold sink. The whole job of the surroundings, the whole job of the cold sink is to cool the gas. So it's to give it a place to put energy and reduce the volume or reduce the pressure. So this heat engine has a high pressure side. We get that high pressure from the hot stuff. And then we need to return it to a lower pressure. That's what the cool sink is for. That's what the surroundings do. They reduce the pressure back down to normal. The hot part increases the pressure or the volume of whatever we're talking about. And because of that, whatever it's increasing the pressure of must be cool to begin with. The gas must start cool. What is the one factor that affects the ideal efficiency of a heat engine? That one factor is the conservation of energy. This is why we cannot exceed a 100%. That's the ideal efficiency of a heat engine, right? So when we're talking about conservation of energy, our big idea here is that machines cannot increase work, right? So they can't make us have more work. In an ideal situation, work in is equal to work out. That's how it works. So the things that affect the efficiency of a real heat engine are heat loss and friction. Those two things always happen, and anytime we lose heat to anything, that reduces work output. The second law of thermodynamics, so with the second law, basically, this is how it's stated in all the books. The universe moves towards a state of disorder. We prefer an increase, spontaneous processes result in more disorder. So for our four consequences, so one of these, and probably the most important consequence, is that heat is going to move from hot to cold. That's the most important consequence. Another thing that happens is that heat is always lost to the surroundings in any process, which means that efficiency is never 100%. It's always less, because we're losing energy, because heat is an energy that we're always losing. And then our last consequence, which is a little bit depressing, is that eventually, eventually all energy becomes heat. That's the so-called third law of thermodynamics, is that all energy eventually turns into heat. Those are our consequences. Why will all the energy in the universe eventually be heat? So all processes result in energy lost as heat. We will eventually run out of energy and it will be turned into heat. Even the processes that we have to produce energy, every single one of those processes requires more energy to produce the energy that we get out, right? So let's say we have a generator that can make 1,000 joules of electric energy. That generator is going to require more than 1,000 joules of energy to make that little bit of 1,000 joules of energy. There's always going to be some heat loss in any process. So, Gerald drops a basketball from a height. It bounces, but doesn't come back to 2 meters. As it continues to bounce, it gets a lower and lower and lower height every time until it doesn't bounce anymore. So, describe the energy transformations of the ball after it is released and it bounces. So, we start off with potential energy at 2 meters. As the ball falls, That becomes kinetic energy. And that's a nice transfer. We're not losing a whole lot there. Maybe a little bit, I'll say this. We lose some energy to air resistance. Then we continue with this transformation. We hit the ground. And in the ground, we have a lot of energy lost to the collision as heat. And then after that collision with the ground, the energy turns back into kinetic energy. That kinetic energy turns back into potential energy. But because of these energy losses, we have less potential energy than we had at the beginning. At every step along the way, we were losing energy, right? So as we fall, we lose energy to air resistance. When we hit the ground, we're going to lose energy in that collision. As we come back up, we're going to lose energy to air resistance. Every step along the way, we're losing energy. That's why we're going to have a lower and lower height. According to the conservation of energy, a warm basketball has enough thermal energy to be transformed into kinetic energy and moved upwards. Why hasn't this happened? So here's the thing about heat energy or thermal energy. Thermal energy is random, meaning that those particles move in different directions. Because those particles move in different directions, because they're random, the total velocity is zero. So they're not moving in the same direction. To bounce up, all of those molecules in the heated ball would move in the same direction. And that one is the opposite of entropy, right? Because that's not disordered, so we would never see that happen. And two, because we're talking about millions upon billions upon trillions of molecules inside of this basketball, getting them all to randomly decide to move in the exact same direction so that the ball has a net kinetic energy from them, or a net momentum from those particles, is statistically impossible. It's never going to happen. So, in this process with the ball, all of the potential eventually becomes heat. So, the U at the beginning turns into Q, or heat, at the end, which means my heat is going to equal my initial kinetic energy. So it's going to be that 0.5 kilogram basketball times 10 meters per second times 2 meters. So the eventual heat that we get is 10 joules, eventually, after it has stopped bouncing. Now, we'll talk about this later, but that's not a lot of heat energy. Heat energy is a very concentrated form of energy, and that's not a lot of heat energy. So, we have a cylinder that holds a liter of an ideal gas at room temperature. 800 joules of heat is added to the gas. So if the gas does no work on the surroundings, that means we have 800 joules in, no work out, so all 800 joules are absorbed. So we dump in 800 joules of heat, but we don't let it expand, we don't let it push anything, and it's just going to absorb all that heat energy. It's going to stay inside of the gas. Nothing's coming out. If the gas does 200 joules of work on its surroundings, we have 800 joules in, 200 joules out, and then 600 joules are left in the gas. So my leftover bit is what's still there. Calculate the efficiency if 200 joules of work is done on the surroundings. So to get efficiency is work out over work in. So the energy that we're putting in, work or energy out over work or energy in. So we're putting into this machine 800 joules of energy, and we're only getting 200 joules out. So 800 over 200 is 0.25, and then to get the efficiency, we have to multiply that by 100%. So it's 25% efficient. That's the efficiency of our machine. Work out over work in. And some of the examples that we may have to do, you might have to calculate your work out. It just depends.